Can you see my screen?
Yes.
Thank you. Let's go.
Good afternoon, students. Today's lecture is dedicated to the fundamental tools that allow us to transition from the logical data model, developed in previous stages, to its physical implementation in a database management system environment. We will examine in detail the data definition language, or DDL, and the data type system, which are the foundation for creating reliable and efficient information repositories. Today, we will proceed step by step from theory to practice. First, we will examine the components that make up SQL and focus on DDL. Next, we will immerse ourselves in the world of data types. This is the foundation upon which the reliability and efficiency of our database is built. After this, we will move to the practical part. We will learn how to create databases and tables, define rules for them using integrity constraints. Finally, we will discuss how to modify existing structures, which is an essential part of the lifecycle of any project. The SQL language is logically divided into several specialized sublanguages, each of which is responsible for its clearly defined group of operations. Understanding this structure is fundamental for consciously using the capabilities of a database management system. The first group of commands, and the key to our today's lecture, is DDL, Data Definition Language, the language for defining data. DDL operators are designed to describe, create, modify, and delete the structure or schema of database objects. It is important to note that DDL commands manipulate not the data stored in tables, but metadata, that is, data about the structure of these tables. Key commands include create for creating new objects, alter for modifying existing ones, and drop for their complete deletion. The second sublanguage is DML, Data Manipulation Language, the language for manipulating data. Unlike DDL, this group of commands is used to directly interact with data stored within tables. The insert command adds new rows, update modifies existing ones, delete deletes, and select retrieves data for further analysis. DML is the topic of our next lectures. The third sublanguage is DCL, Data Control Language, the language for managing data. This category of commands is responsible for aspects of security and management of user access rights to objects and data in the database. The grant command grants users certain permissions, for example, to read or write to a table. The revoke command accordingly revokes these permissions. The last group is TCL, Transaction Control Language, the language for managing transactions. A transaction is a logical unit of work that can consist of a series of DML operations. TCL allows managing these transactions to ensure data integrity. The commit command fixes all changes made within a transaction, making them permanent. The rollback command cancels all changes, returning the database to its state at the start of the transaction. In this way, DDL is the starting point from which the life cycle of any database begins, since its operators create the framework for the future data storage. We will focus on this sublanguage today. In previous stages of design, the concept of domain integrity was introduced as one of the three key guarantees of the relational model. A domain defines a set of valid values for a certain attribute. At the physical level, this theoretical concept is realized precisely through the system of data types. When we create a table, we are obliged to clearly specify the type of each column. This is the principle of strict typing, and it provides us with several fundamental advantages. First, it is a powerful mechanism for ensuring data integrity. The system simply will not allow a text string to be written into a column defined as numeric. This basic level of validation is delegated directly to the database, which is a much more reliable approach than relying solely on checks at the application level. Second, it is a question of resource distribution efficiency. Knowing the exact data type, the database can optimally allocate disk space and RAM. For example, for storing a person's age, a 1-byte integer type is sufficient, while for a transaction identifier in a large system, an 8-byte type may be needed. An incorrect choice of type leads to excessive resource utilization and can negatively impact performance. Finally, data types guarantee the correctness of operation execution. The database understands that arithmetic operations can be performed on numeric types, while date types can be used to calculate intervals. This prevents incorrect manipulations and ensures the expected behavior when sorting and comparing values. Although the standard SQL defines a basic set of types, each database system implementation, such as MySQL or PostgreSQL, has its own extensions. Next, we will discuss the main categories of data types that are common to most systems. The first and most common category of data types is numeric. We will start with types designed for storing integers. The key difference between them is the memory size allocated for storing the value. This size directly defines the range of valid values. The correct choice of type allows significantly optimizing disk space usage, which is especially important for large tables. Let's consider them sequentially, from the smallest to the largest. Tiniant occupies only 1 byte. Its range is very limited, from -128 to 127 for signed numbers, or from 0 to 255 for unsigned and signed. This type is ideal for storing data where the range of values is known and small, for example, age, family size, or what is very common for emulating Boolean values where 0 is interpreted as false and 1 is true. Smallint occupies 2 bytes. The range is much wider, up to 32,000 for signed numbers. This is a good choice for attributes such as the number of pages in a book, auditorium capacity, or car production year. INT, or its synonym integer, occupies 4 bytes. This is the most universal and common integer type. Its range, which exceeds 2 billion for signed numbers, is sufficient for most scenarios. INT is most often used for surrogate primary keys, that is, ID columns in most tables. Bigint occupies 8 bytes and is designed for storing extremely large integers, measured in quintillions. Its use is justified only in high-load systems where the number of records in the table may exceed billions, for example, transaction identifiers in a global financial system, or in specific scientific calculations. General rule to follow. Always choose the smallest data type that can guarantee containing all possible values of your attribute. This directly affects the size of the database, index speed, and the amount of data transferred between disk and RAM. Now let's consider the types designed for storing numbers with the fractional part. Here, the choice is fundamental because it affects the accuracy of calculations. There are 2 fundamentally different categories of these types. The first and extremely important category is fixed point types, represented by decimal and its synonym numeric. Their key feature is that they store the exact decimal value. Internally, the DBMS represents such a number essentially as a string of digits, which completely eliminates the rounding errors inherent in binary floating point formats. The syntax decimal PS allows us to precisely control the total number of digits, P precision, and the number of digits after the decimal point, S scale. This makes decimal the only acceptable and professional choice for any financial calculations: commodity prices, transaction amounts, interest rates, exchange rates. The second category is floating point types: float, single precision, and double precision. They store approximate values, representing the number in scientific notation with a mantissa and an exponent. This approach allows covering a huge range of values with a relatively small amount of memory. However, due to the peculiarities of the binary representation of fractions, they are inevitably prone to slight rounding errors. For example, the number 0.1 cannot be represented exactly in binary format. Therefore, never use float or double to store money. The accumulation of such microscopic errors during aggregate calculations, for example, when calculating the total sales, can lead to significant discrepancies in financial reports. The scope of their application is scientific and engineering calculations, where absolute accuracy is not as critical. Physical measurements, statistical data, geographic coordinates. String data types are designed to store text information. The fundamental division of these types is based on the storage principle, fixed or variable length. The first type is char-n, which means a fixed length string. When we define a column as, for example, char10, the database management system always reserves exactly 10 bytes on the disk to store the value, regardless of the actual length of the string. If we write the word SQL there, which consists of 3 characters, the system will pad it to 10 characters with spaces. This approach can provide a slight performance gain for data that is guaranteed to have the same length, since the DBMS does not need to calculate the position of the next record. Its scope of application is fixed-length codes, 2-letter country codes UA, hash sums, phone numbers in a uniform format. The second and much more common type is varchar-n, a variable length string. Unlike char, it stores only the characters that were actually transmitted, plus 1 or 2 bytes of auxiliary information to store the length of the string itself. This makes varchar much more efficient in terms of disk space usage for the vast majority of text data whose length varies. First names, last names, addresses, product names. This is the most universal string type. And the third category is the text family of types. They are designed to store large text objects. The body of a blog article, a full description of a product, the content of a comment. An important technical detail is that in many DBMS, text type data is stored separately from the main table row. This avoids slowing down table scanning operations when these large text fields are not needed in the query. When working with string data, it is not enough simply to choose the varchar type. There are 2 related concepts that are defined at the database, table, or column level, and are fundamental for correctly working with international data. The first concept is a character set or encoding. This is, essentially, a table of correspondences that matches each character, letter, number, punctuation mark, with a unique numeric code that is stored in the computer's memory. An incorrect choice of encoding will inevitably lead to problems. For example, if you choose an outdated encoding Latin one, you simply won't be able to store Cyrillic letters in the database. Instead, you will get question marks or other unreadable symbols. The modern industrial standard is UTF-8 MB4. It is a superset of popular UTF-8 and supports practically all languages of the world, as well as special characters and emojis. For all new projects, you should without hesitation choose UTF-8 MB4. The second concept is comparison rules or collation. This is a set of rules that tell the system how to compare and sort strings. The collation name usually contains the name of the encoding and a special suffix. The most important suffixes, _CI, case-insensitive means that comparison is case-insensitive. With such collation, strings Pedrenka with a capital letter, Pedrenka when all letters are lowercase, and Pedrenka when all letters are uppercase will be considered the same. This is the most common variant for most applications, since it simplifies searching. _CS, case-sensitive, means that comparison is case-sensitive. With such collation, strings Pedrenka with a capital letter, Pedrenka when all letters are lowercase, and Pedrenka when all letters are uppercase will be considered different. _bin binary executes the fastest but primitive comparison, simply compares the numeric codes of the bytes of the characters byte by byte. With such comparison, a uppercase does not equal a lowercase. So, when creating a database or table, the correct choice for working with Ukrainian and other languages will be, for example, UTF-8 MB4 for encoding and UTF-8 MB4 _Unicode _CI for comparison rules. Saving time information is a fundamental requirement for most systems. Trying to store dates or times in non-specialized types, such as varchar or int, is a gross architectural error. Such an approach makes validation, correct sorting, and using built-in functions of the DBMS for arithmetic operations, for example, calculating the interval between two dates, impossible. Let's look at the native types that SQL provides. Date, the simplest type that stores only the calendar date. Year, month, day. The time component is missing. It is optimal for attributes that fix an event for which time is not important. Birth date, publication date of a printed edition. Time stores time of day, hours, minutes, seconds. An interesting feature is that it can represent not only a specific time but also a duration, so its range in some DBMS, such as MySQL, can be much higher than 24 hours. Datetime stores a combination of date and time. The value does not depend on the time zone. This is the most common variant for most applications, since it simplifies searching. Timestamp also stores date and time, but the value depends on the time zone, stored in UTC. Standard for system fields, created _at, updated _at. Concluding the overview of data types, let's look at two more categories. The first is the logical or Boolean type. It is designed to store truth values, true or false. This type is fundamental for building conditions in queries and implementing business logic, for example, for is_active or is_published attributes. It is important to know that in MySQL, the Boolean type is simply a synonym for the smallest integer type int. 1. By convention, the value 0 is interpreted as false, and any non-zero value, usually 1, as true. It is also worth remembering about SQL's three-valued logic. If a column does not have a not null constraint specified, it can contain null, which means unknown or indeterminate, and is not equivalent to false. The second category is types for binary data, known as blob, binary large object. They are analogs to the text family, but with a key difference. Blob data is stored as a raw byte stream, without any character interpretation or encoding application. They are designed to store files, images, documents, audio recordings. However, here I must emphasize the modern approach to storing files. Although the technical possibility of storing files in a blob exists, it is considered a bad practice for most web applications. Storing files in a database leads to rapid growth of its size, which complicates backups, and to performance degradation. A database server is not optimized for transmitting large file streams. The modern best practice is to store files in the file system on a server or in cloud storage, for example, Amazon S. Only a text string varchar, with the path to this file or its URL. This approach allows the database to remain compact and fast, and files to be served via web servers optimized for this. After we have decided on the data types for the attributes of our logical schema, the next step is its physical implementation. This process begins with the creation of the main container, the database. A database is an isolated space that contains a related set of objects, tables, indexes, procedures, etc. The fundamental DDL command for this is create database. Let's break down its syntax. The main construct is create database, followed by a unique name for our database. Next comes the optional but very useful directive if not exists. It tells the system to create the database only if an object with this name does not already exist. This avoids an execution error if, for example, you are rerunning a script to set up the environment. And the most important part is the character set and collate parameters. As we discussed earlier, they set the default encoding and comparison rules. All tables that will be created in this database will inherit these settings. Therefore, the correct definition of these parameters at the very beginning is critically important for unified and correct work with string data throughout the project. Let's look at a practical example. Let's look at what a real command to create a database for our hypothetical university project looks like. The command starts with create database if not exists, which is a safe way to write it. Next, we give the database a semantically meaningful name, university_db. The next two lines are the most important from the perspective of long-term project support. We specify character set UTF-8MB4. As I already emphasized, this is the modern standard that guarantees that we can store data in any language, whether it is Ukrainian, English, or any other, and also process special characters and emojis without the risk of data loss or the appearance of unreadable characters. Next, we set collate UTF-8MB4 for Unicode_. This parameter defines the comparison rules. The suffix means case-insensitive, i.e. not sensitive to case. This means that when searching or sorting, the system will not distinguish between uppercase and lowercase letters, which is the expected behavior for most applications. For example, a search by the surname Shevchenko in lowercase will find both Shevchenko, with the first letter capitalized, and Shevchenko in all caps. Executing this single command creates an empty but correctly configured database, ready to be filled with tables. After creating the container, the database, we move on to creating the main objects for storing structured data, which are tables, or, if using the terminology of relational algebra, relations. Before creating a table, you must explicitly specify which database we are working in. For this, the use command is used, followed by the database name, for example, use university_db. After executing this command, all subsequent DDL operations will be performed in the context of this database. The command to create a table itself is create table. As with create database, the if not exists directive can also be used here to avoid errors. In the body of the command, in parentheses, we list the definitions of all columns of the future table. Each such definition consists of at least two components: column name, a unique identifier of the column within the table; data type, one of the types we discussed in detail earlier. It is at this stage that we physically implement the designed logical model by assigning a specific data type to each attribute. Also, each column definition can contain optional integrity constraints, such as primary key or not null. They are extremely important, and we will dedicate a separate section of our lecture to them a bit later. For now, let's look at an example of creating a simple table without complex constraints. Let's apply our knowledge of data types in practice and create our first table, students. First, we execute the use university_db command to specify that all subsequent operations should take place in this database. Next comes the create table students command itself. In its body, we define the columns, which are the physical implementation of the attributes of the student entity. For student_ID, we choose the int type. This is a standard choice for a unique identifier in a medium-sized table. For first_name and last_name, we use varchar 50. Varchar is chosen because names and surnames have different lengths, and this type efficiently uses space. The 50-character limit is sufficient for most cases. For birth_date, we use the specialized date type, which will allow us to correctly store the date and perform operations on it in the future. For GPA grade point average, we choose decimal 3-2. This is a fixed point type that guarantees precision. The parameters 3-2 mean that the number can have a total of 3 digits, 2 of which are after the decimal point. For example, 4.50 or 3.98. And finally, for is_active, we use the Boolean type to indicate whether the student is currently active. As we remember, in MySQL, this will be implemented via Tiniant 1. At this stage, we have created the skeleton of the table. It can already accept data, but it does not yet have any rules that ensure its uniqueness, mandatory nature, or relationships. These rules are implemented using integrity constraints, which we will now consider. On previous lectures, we introduced the fundamental guarantees of the relational model: entity integrity, referential integrity, and domain integrity. Until now, we have talked about them as theoretical concepts. Now we will look at how these concepts are implemented in practice. The tool for this is integrity constraints, or simply constraints. These are declarative rules that we add to the table definition. They instruct the database management system to automatically control the data being added, changed, or deleted. If any DML operation, insert, update, or delete, attempts to violate one of these rules, the DBMS will reject the operation and return an error. For example, if we define that the email column must contain only unique values, the system will simply not allow inserting a second record with the same email. It is important to understand that implementing these rules at the database level is the most reliable way to ensure data integrity. Of course, checks can also be implemented in the application code, but constraints at the DB level are the first and strongest line of defense. They will work regardless of which client connects to the database, whether it is a web application, an analytical tool, or direct administrator queries. Next, we will sequentially consider the main types of constraints: primary key, foreign key, unique, not null, and check. The first and most important constraint we will consider is primary key. It is a direct physical implementation of the theoretical principle of entity integrity, which states that each entity, row in a table, must be uniquely identifiable. When we designate a column or group of columns as a primary key, we impose two implicit rules on it. First, all values in this column must be unique. Second, no value can be undefined, null, not null. The combination of these two rules guarantees that we will always have a reliable and unambiguous way to refer to any specific row in the table. It is important to remember that a table can have only one primary key. There are two ways to define a primary key. If the key is simple, i.e., it consists of one column, it can be specified directly in the definition line of that column. If the key is composite, i.e., a combination of values from several columns is required to uniquely identify a row, then its definition is moved to the table level after the list of all columns. Let's look at the syntax with examples. Let's analyze the syntax using two key examples. The first example demonstrates the creation of the students table with a simple primary key. We see that the primary key constraint is added directly in the definition line of the student_ID column. This is the simplest and most readable method for single column keys. Note the additional auto_increment directive. This is a standard industrial approach for generating surrogate primary keys. It instructs the DBMS to automatically generate a unique sequential numeric value for this column when each new row is inserted. Thus, we do not need to worry about generating and ensuring the uniqueness of identifiers manually. The second example shows the enrollments table, enrollment in a course. In this table, neither student_ID nor course_ID alone can be a primary key, since one student can be enrolled in many courses, and many students can be enrolled in one course. However, the combination of student and course is unique. A student cannot be enrolled twice in the same course. Therefore, here we use a composite primary key. To define it, table-level syntax is used. After listing all the columns, we add a separate primary key line and list all the columns that make up the key in parentheses. For composite keys, such syntax is the only one possible. The next most important constraint is foreign key, or foreign key. It is a practical implementation of the principle of referential integrity. If the primary key ensures uniqueness within one table, the foreign key creates and maintains logical relationships between different tables. In the context of this relationship, we distinguish two tables. The parent table, the one being referenced, it contains the primary key, and the child table, the one that references, it contains the foreign key. The main task of a foreign key is to guarantee that for every record in the child table, there is a corresponding record in the parent table. For example, if we have an enrollments child table with a reference to the courses parent table, the foreign key constraint will not allow adding a course enrollment record with an identifier that does not exist in the courses table. This prevents the appearance of so-called orphan records, data that refers to something that no longer exists. An important technical requirement is that the data type of the column you define as a foreign key must exactly match the data type of the column it references in the parent table. Also, the reference column in the parent table must necessarily be a primary key, or have a uniqueness constraint, unique. Let's see how this works. To create a relationship, we need at least two tables. First, we create the parent table courses. It contains a unique list of all available courses. The course_ID column is defined as primary key, and this is what we will reference. After that, we create the child table enrollments. It contains information about student enrollment in courses. Pay attention to the last line in the definition of this table. This is the syntax for creating a foreign key. Let's break it down in detail. Foreign key, course_ID. Here we specify which column in the current child table enrollments will be the foreign key. References courses, course_ID. Here we specify which parent table, courses, and which of its columns, course_ID, are foreign key references. After creating these tables with such a constraint, the database management system will strictly monitor referential integrity. This means that you physically will not be able to add a record to enrollments with a course_ID that does not exist in the courses table. Similarly, by default, you will not be able to delete a course from the courses table if it is still being referenced by records and enrollments. In this way, we reliably protect the data from logical inconsistencies. The unique constraint ensures the uniqueness of values in a column, similar to primary key, but has several key differences and a different scope of application. It is used to implement business rules where a certain attribute that is not a primary key still needs to be unique. Classic examples are a user's email, phone number, login. Let's break down its differences from the primary key. First, while there can be only one primary key in a table, multiple unique constraints can be defined. Like in our example with the users table, where we need both username and email to be unique. Second, it is the attitude towards null. A column that is a primary key is implicitly not null, meaning it cannot contain undefined values. In contrast, a column with a unique constraint can contain null. Usually, only one null value is allowed because in SQL logic null does not equal anything, even another null. This allows having, for example, unique passport numbers, while allowing some users not to specify this number. Regarding the syntax, as with the primary key, the constraint can be defined in two ways. The first is at the column level, as we see for username. The keyword unique is simply added at the end of the line. The second is at the table level, as for email. Both methods are equivalent for simple single-column constraints. Now let's look at two constraints that directly implement domain integrity. That is, ensure that the data complies with the specified rules. The first is not null. This is one of the simplest and most commonly used constraints. It prohibits inserting null values into a column. That is, when adding a new row, this field must be filled in. In the students table, for example, it would be logical to apply not null to the first underscore name and last underscore name columns, since a student cannot exist without a first or last name. The second and more powerful constraint is check. It allows you to define your own logical condition that all values in the column must satisfy. This condition can be quite complex. Let's look at the example of the products table. For the price column, we applied two constraints at once. Not null, which makes the price mandatory, and check, price equals 0, which prohibits entering a negative price. The DBMS will check this condition every time you try to insert or update a record. For the status column, we use check with the IN operator. This constraint allows you to insert into the status column only those values that are in the specified list, available, or out_of_stock. This is a good alternative to creating a separate reference table for simple lists. Thus, by combining these constraints, we shift the responsibility for maintaining basic data integrity from the application code to the DBMS itself, which makes the system much more reliable. Changing business requirements or optimization inevitably lead to the need to change the table structure. The DDL language provides the powerful alter table command for this, which allows you to modify an existing table without the need for its complete recreation and data loss. Let's look at the two most common operations. The first is adding a new column using the add column directive. In the example provided, we are adding a new email column to our students table. We immediately define its data type as varchar 100 and the unique constraint. Also, note the optional after last _name directive, which specifies exactly where in the table structure the new column should appear, improving the readability of the schema. The second operation is deleting a column using drop column. This operation is much more dangerous. In the example, we are deleting the GPA column from the students table. I must emphasize that this operation is irreversible. Along with the column, all data contained in it will be permanently lost. Before performing such an operation on a real database, you must be absolutely sure of your actions. In addition to adding and deleting columns, alter table allows you to perform more fine-grained adjustments. The first operation is modify column. It allows you to change the definition of an existing column, its data type, set of constraints, or default value. In our example, we are modifying the last _name column in the students table. We are increasing its maximum length to 75 characters and adding a not null constraint, making this field mandatory. Here you should be careful. When changing the data type to a less capacious one, for example, from varchar 100 to varchar 50, data loss due to truncation may occur. The second block of operations is flexible management of integrity constraints. We can add and delete them after the table has been created. To add a constraint, the add constraint syntax is used. In the example, we are adding a foreign key to the enrollments table. Note fk_enrollments_students. This is the name we give to our constraint. Giving meaningful names to constraints is a very good practice, as it allows you to easily refer to them in the future. Accordingly, to delete a constraint, the drop constraint command is used, followed by the name of the constraint we want to delete. This demonstrates why naming constraints is so important. Without a name, it would be difficult for us to identify which specific rule to delete. The last DDL command in this section is drop table. This is one of the most dangerous commands in SQL, so it should be used with extreme caution. The drop table command completely and irreversibly deletes a table from the database. This means that not only its structure metadata is deleted, but also absolutely all rows of data that were stored in this table. Along with the table, all related objects, such as indexes, are also deleted. This operation is irreversible. It is impossible to restore a deleted table using standard SQL tools. This requires recovery from a backup. The syntax of the command is very simple. Drop table, followed by the table name. As with create commands, it is also appropriate to use the if exists option here. It prevents an error if you try to delete a table that no longer exists, which is useful when executing scripts. Before executing drop table on any database other than a test one, you must be absolutely sure of your actions. Accidental deletion of a working table can lead to catastrophic consequences for any application. Now, to consolidate the material we've just covered, let's check our understanding. I propose you think about 3 questions that cover the key aspects of today's topic. The first question concerns the structure of the language itself. Which SQL sublanguage is responsible for creating, modifying, and deleting the structure of database objects? The second is about data types, and this is a very important practical point. What is the key difference between the timestamp and datetime data types? And the third question connects theory with practice. Which integrity constraint implements the entity integrity principle, ensuring unique identification of each row in the table? These are just a few key points. You will find a more extensive list of self-check questions in the lecture notes. I strongly recommend that you go through the entire list to better prepare for the practical assignments and the exam. That concludes our lecture on data definition language and data types. We have covered the fundamental tools that allow you to create and manage the structure of databases. Thank you for your attention. If you have any questions about today's material, my contact information, email address, is displayed on the screen. That's all for today. Have a great day.